In the realm of modern physics, few facilities have captured the public imagination quite like CERN's Large Hadron Collider, LHC. This marvel of engineering and scientific innovation has been the subject of numerous discussions, both within scientific circles and among the general public. However, alongside legitimate scientific discourse, a range of misconceptions and speculative theories have emerged. Let's examine what the LHC actually does, address some common misconceptions, and explore its genuine scientific achievements. The Large Hadron Collider is the world's largest and most powerful particle accelerator. Located near Geneva, Switzerland, it consists of a 27-kilometer, 17-mile, ring of superconducting magnets situated between 50 and 175 meters, 165 to 575 feet, underground near the French-Swiss border. The LHC was designed to accelerate particles to nearly the speed of light and then collide them to create conditions similar to those moments after the Big Bang, allowing scientists to observe fundamental particles and forces that shape our universe. The primary scientific goal of the LHC has been to test predictions of theoretical physics, particularly those related to the Standard Model, the theory that describes the fundamental particles and forces of nature. One of its most celebrated achievements was the discovery of the Higgs boson in 2012, confirming a long-standing theoretical prediction about how particles acquire mass. Contrary to claims that the LHC creates portals to parallel universes, the actual purpose of the machine is to study the fundamental building blocks of matter within our universe. While physicists do theorize about the possibility of multiple universes, the multiverse theory, these remain theoretical concepts, and the LHC was not designed to access them. The particle collisions that occur in the LHC create extremely small, highly controlled energy events that allow scientists to observe subatomic particles. These events are monitored using sophisticated detectors that record data for analysis. They do not create gateways to other dimensions or realities. Before the LHC began operations, concerns were raised about the possibility that it might create microscopic black holes that could pose a danger to Earth. These concerns were thoroughly addressed by the scientific community, including in a comprehensive safety report published by CERN. Physics calculations show that any microscopic black holes that might theoretically be produced would instantly evaporate through a process called Hawking radiation. Moreover, cosmic rays that naturally bombard Earth have been creating similar high-energy collisions in our atmosphere for billions of years without catastrophic consequences. The LHC's operations have confirmed these safety assessments, operating successfully since 2008 without producing any dangerous phenomena. One of the genuine scientific mysteries that the LHC is helping to investigate is dark matter. This invisible substance makes up approximately 27% of the universe, yet we cannot directly observe it with conventional instruments. Its existence is inferred from gravitational effects on visible matter and the structure of the cosmos. During its operational runs, the LHC has searched for particles that might constitute dark matter. While the definitive nature of dark matter remains elusive, the data collected contributes valuable information to this ongoing investigation. Scientists hope that further research at the LHC might eventually shed light on this cosmic mystery. A genuine scientific development at CERN has been the study of X-particles within quark-gluon plasma. In January 2022, scientists at CERN reported identifying these rare particles among billions of others produced in high-energy lead-ion collisions. X-particles are believed to have existed briefly in the earliest moments after the Big Bang, when the universe was an extremely hot plasma of quarks and gluons, the elementary particles that later combined to form protons and neutrons. By recreating these conditions in the LHC, scientists can study how these particles behaved and interacted during the universe's formation. This research helps physicists understand the fundamental forces and particles that shaped our universe in its earliest moments. A legitimate and fascinating scientific endeavor that doesn't require invoking parallel universes or dimensional portals. The text referenced the Mandela effect, a term coined by Fiona Broome in 2009 to describe collective false memories. The classic example involves people who incorrectly remember Nelson Mandela dying in prison in the 1980s, when in fact he was released from prison in 1980-1990 and died in 2013. While this phenomenon is real and documented, It's important to understand that cognitive scientists and psychologists attribute it to the fallibility of human memory, social reinforcement of false information, and the power of suggestion, not to shifting between parallel universes. The Mandela effect is an interesting psychological phenomenon, but does not constitute evidence for theories about parallel realities or universe shifting. The LHC has completed several successful operational runs, with notable achievements including the discovery of the Higgs boson in 2012, confirming a major prediction of the Standard Model. Observations of rare particle decays that help refine our understanding of fundamental physics. Studies of quark-gluon plasma, providing insights into conditions shortly after the Big Bang. Discovery of several new composite particles that expand our knowledge of how quarks combine. After its second operational run, ended in 2018, the LHC underwent maintenance and upgrades. It resumed operations in April 2022, with its third run commencing in July 2022. The LHC is scheduled to continue operating until 2025, after which it will undergo another 2-year shutdown for further modifications. Scientists hope these ongoing improvements will allow the LHC to probe even deeper questions in physics, potentially offering insights into supersymmetry, extra dimensions, and the nature of dark matter, all within the framework of rigorous, evidence-based scientific inquiry. When evaluating claims about cutting-edge physics research, it's essential to distinguish between peer-reviewed scientific work and speculative theories. Genuine scientific advances. 1. Are published in peer-reviewed journals where other experts can evaluate the methods and conclusions. 2. Offer testable predictions that can be verified or falsified through additional experiments. 3. Build incrementally on established knowledge, even when proposing revolutionary ideas. 4. Acknowledge limitations and uncertainties rather than making absolute claims. The actual work at CERN represents some of humanity's most sophisticated efforts to understand the fundamental nature of our universe. This research is both profound and challenging enough without adding unfounded claims about parallel universes or reality shifting. The Large Hadron Collider represents one of humanity's greatest scientific and engineering achievements, a tool that allows us to probe the fundamental nature of matter and energy. The actual discoveries being made at CERN are far more fascinating than speculative theories about parallel universes or dimensional portals. By understanding what the LHC actually does and the legitimate scientific questions it helps answer, we can appreciate the true wonder of modern physics research, a collaborative, evidence-based endeavor that continues to expand our understanding of the universe in which we live. This appreciation doesn't require sensationalism or misconceptions. The reality of cutting-edge physics is already extraordinary enough.